Welcome back to Inorganic TUTOR'S Institute. In today's lecture, we are going to dive into 3 special problems from differential equations. Alright, so basically our first problem is we want to verify that 1 over this function is an integrating factor of this differential equation. Hence, we want to solve this differential equation by differentiating the equation integral of this function plus ln into x over y equals c. All right, so before we begin this journey, I want you to know some basic definitions before we start the process, right? So when I want you to know that when a differential equation isn't exact, or when a differential equation is not exact, that is not the total differential of some functions, we can sometimes multiply it by a function called the integrating factor. Okay, we can sometimes multiply it by the integrating factor to make it exact. Okay, to make it exact, right? So that means after multiplication, the new equation becomes the total differential, right? So after your multiplication, then the new equation becomes your what? Total differential. So your new equation becomes your total differential of the function, right? So that equals 0 and equals what? C. So if the total differential is now equals this, then we can solve this phi of x and y equals what? A constant, right? So now let's look at the problem at hand, right? Let's look at the problem at hand. So the problem is by differentiating the equation integral of what? This function plus ln of x over y equals what? C. Right. So this equation that we see here depends on only the product of two functions, the product of x, y. Okay, so this function that we see here depends on the product of only x and y, right? Depends on the, okay, so once this function depends only on the product of this function x, y, then we have to take a very good look at this function x, y. Okay, so first of all, we want to verify that 1 over x, y, all multiplied by small f of x, y minus big F of x, y is an integrating factor, right? So an integrating factor, we already know that an integrating factor, and then we can use it to solve the equation, right? If this is an integrating factor, then we can use it to solve the equation, right? So we have to check that. Okay, so let's begin with the verification. So we are beginning with the process. All right, so this is our function that we know here. I don't want to rewrite the function because it's too lengthy, right? So first of all, from this function, let's say that I of x and y, or mu of x and y, should be equal to the integrating factor, which is 1 over xy multiplied by small f of xy minus big F of xy, right? So that is what we have. So we are saying that this function that we see here, what they are saying that we should verify should be equal to what? Mu of x and y, or I of x and y because that is an integrating factor. So an integrating factor, some notations are I, or you can use mu of x and y. They are all the same. So now let's try to name this equation 1, f of x y times y dx plus big F of x y x dy equals 0. We are naming that equation 1. Okay. All right. So that is our equation 1. Now, step 2. So this is our step 1. Don't forget. Once you let this integrating factor equals what? I of x comma y, or mu of x comma y, which is equal to the function that you have been given. Then step 2, don't forget that this integrating factor is an integrating factor of the function, this function that we have named it equation 1, right? So secondly, I want to remind you again, an integrating factor converts a non-exact differential equation to an exact differential equation, right? So that is after multiplication, right? So now let m of x and y be equal to this function, right? That is f of x, that is f of x y times y, okay? F of x y times y, and then let n of x y equals big F of x y times x, right? So if this is our differential equation, then the first term here becomes our m of x and y, right? Then our second term becomes your n of x and y. All right, so once we know that, then what we have to do is that we have to multiply this equation right here by the mu of x, right? So we multiply equation 1 by mu of x and y, or I of x and y. Okay, so we are going to use this to multiply this, right? Are we clear with that? So because that is the integrating factor. Okay, so we are going to do that here. So we multiply that. So we're going to have f of x y multiplied by y times dx. Then this will be xy multiplied by f xy minus big F of xy, right? Plus big F of xy times dx, all divided by xy small f of xy minus big F of xy times dy. Okay, so that should be equal to what? 0. All right, so now let's simplify that. You know, when you simplify that, this will take all of this, and then this also take all of this, right? So we're going to have f of x y dx all over x into small f fxy, big fxy plus big fxy dy all over y into small fsy minus big fsy dy, and that still equals 0, right? So we have been able to simplify after multiplying the integrating factor by what? The equation 1, right? So now, since this function is a product of only x and y, then I want us to use that x and y, xy effectively, right? So I want us to say that let u equals xy. Okay, so if u equals xy, I want to clean this here. So if u equals xy, then we can say that that implies that when you differentiate with respect to u will be equal to, we are using the product rule, okay? Differentiate with respect to u. On the other side, use the product rule, you maintain x, or you say you differentiate x, then maintain y, plus differentiate y, then maintain x, right? So this is what we have. Now, I want us to work this algebraic expression so that we have an expression to substitute here, because that is our mission. Okay, so here we divide by u, we divide all this by u. So we're going to have du, and don't forget that u is what? Xy. So we're going to have dxy all over xy equals y dx plus x dy all over xy, right? So this means that we're going to have d of xy over xy equals, when you split these terms, we're going to have y dx over xy plus x dy over xy, right? So this will take care of this, and also this also takes up this. So we're going to have d of xy over xy, and that is equal to vx over y plus vy over, vx over x plus dy over y. So we have this. Note that down, it's very important. We are going to use it somewhere. So you can see that we have d of xy over xy equals this expression. So that means that when you are coming here, we are coming to substitute d of xy over xy. We will replace it with this expression. So whole lift here. You see the angle we are heading towards to. So when we come here, we're going to lift this and substitute here, right? So let's move on. Let me take care of this. So once we said that u should be equal to xy, then it means that we can also say that small f of x y should be equal to what? F of what? U, right? Because we are saying that xy should be what? U. So wherever we see that xy, we put what? U, right? The same thing applies to the big F of xy. That will be equal to big F of U, right? So we have that info, right? So the next thing we have to do is we have to equate equation 2. Yeah, right. So we're going to have fu, where we're having from equation 1, right? We're having f of xy divided by x of small f of xy minus big F of xy multiplied by the x plus big F of xy divided by y multiplied by fsy minus multiplied by dy, right? And this is equal to what? 0. So this was what? Our equation 1. Now, we've said that f of xy should be equal to what? F of u. So wherever we see xy, f of xy, put what? F of u. Same thing applies to the big F of u. So we're going to put that there. So we're going to have f of u over x into f of u minus big F of u, all multiplied by the x plus big F of u all over y into small f of u minus big F of u dy equals what? 0. So we consider this to be what? Equation 2. Right. So we have simplified. This was our equation 1. We have simplified that to equation 2 by substituting f sy equals what? Fu in place. Right. So now let's move up here. I don't want to clean this because we are going to use it. So let me write that here. Dxy over xy is equal to the x over x plus the y over what? Y. So note this information is very useful. So let me clean this. So now let's take the differential of the function, right? Let's take the differential of the function, right? This is the function that we are trying to differentiate. Integral of this function, want to integrate. So we want to differentiate. So let's do that. So let's take the differential of the function. Right. So when we do that, that means that we are going to differentiate this, right? So phi of x comma y is equal to, we're going to differentiate this, right? So that will be equal to integral f x y. Already we say that this should be u, right? So fu plus fu over fu minus fu times the xy. I wanted to substitute that straightforward, but there is no right. Let's try to minimize this so that we can write that straightforward, right? So we have integral f of u plus big F of u all over small f of u minus big F of u times, now this here is here, right? So we're going to replace that, say dx over x plus dy over what? Y, right? Plus ln into x over y, and that is equal to phi of s and y, right? So I want us to handle this natural log function before we start the whole process, right? So we're going to handle this. So when you differentiate the natural log function, ln into x over y, it can be expressed as ln into x minus ln into what? Y, right? So we have differential of ln x minus differential of ln y, right? So basically, so we're going to have differential of ln x minus differential of ln y. Don't forget, if you want to differentiate a ln function, a function inside the ln, you take 1 over the function times differential of the function, then minus 1 over the function times differential of the function, the inner function, right? So we took 1 over x, which is here, times differential of what? X, minus 1 over y times differential of what? Y. So this is what we have. So we're going to substitute this in place of what? This, right? So we're going to have integral small f of u plus big F of u all over small f of u minus big F of u times dx over dx plus dy over y plus this, right? So we're going to have 1 over x dx minus 1 over y dy. Okay, so this is what we have so far. Now, what do we do next, right? So this, we can see that we can do some groupings, right? We can group terms, right? So let's try to do that from here. Okay, so we say that integral f of u plus big F of u all over small f of u minus big F of u times 1 over x plus 1 over x all the x plus f of u plus big F of u all over small f of u minus big F of u times 1 over y minus 1 over y dy. Okay, so this is what we have. Now, what do? We have to simplify this, simplify this. Okay, so now factorizing the dx and the dy out, we're going to have big brackets into 1 over x multiplied by small f of u plus big F of u all over small f of u minus big F of u, right? Plus 1. Plus 1. Right? Then all the x. Then plus the second part, which is the dy part, we factor 1 over y out, right? Then into f of u plus big F of u all over small f of u minus big F of u minus 1. Then this becomes dy, right? And this is equal to the total differential of phi, right? So now that we have this, we can see that we have common what? We can multiply through by this, right? We can multiply through by this to make sure that this one to this thing is affected by the one, and also this part too, we can multiply through so that make sure this thing is affected. So we're going to have total differential of phi to be equal to big brackets 1 on x into f of u, small f of u plus big F of u plus f of u minus f of u, right? All over small f of u minus big F of u, right? Okay. Now this is closed. Then we have the x plus, we do the same thing here. So let's go up. Let's go up. So we're going to do the same thing there. So plus 1 over y into f of u plus big F of u minus into f of u minus big F of u all over small f of u minus big F of u. This is all dy, right? So we started from here, started a process from here. So now let's try to expand that. So this implies that total differential of phi will be equal to big brackets 1 on x. Then we open our brackets. You know, when we open the bracket, this f of u, small f of u plus big F of u plus small f of u minus big F of u, this will take care of this. So the big F of u is off. So we're going to have f of u plus f of u small, right? So all over small f of u minus big F of u, right? Or the x, right? We're going to do the same simplification for the second part, which is into 1 on y, then f of u plus big F of u minus f of u plus big F of what? U, all over small f of u minus big F of u, right? So this all multiplied by dy, right? So we have our total differential of phi to be equal to 1 on x into small f of u plus small f of u have what? 2f of u, right? Divided by 2 divided by f of u minus big F of u, or the x, right? Plus 1 on y into small f of u, positive and negative f of u goes off, right? So we're going to have 2 big F of u all over small f of u minus big F of u, right? Or dy. Okay, so this is where we've gotten to so far. So what can we do with this? This is what we got into. So this is our total differential, right? So with this, what can we do so that we get let's try to write this expression here. So we have our differential now becomes 2 times small f of u all over x into small f of u minus big F of u, right? This times the x plus 2 big F of u all over y into small f of u minus big F of u, right? So we have that dy, and this is what we have. All right, so what can we do here right now? We can see that we have a coefficient 2 common to all. So let's divide both sides by 2, right? So when we do that, we're going to have our total differential to be equal to f of u, small f of u over x into small f of u minus big F of u dx plus big F of u over y into small f of u minus big F of u times dy. Okay, so this is what we have right now. So this is our differential. This is what our differential has become, right? So if we are to write this thing continuous, we would have said that this and this is our LCM, right? So now let's try to, if this and this are our LCM, then let's try to multiply through by xy of small f of u minus big F of u, right? So we're going to do that. Right? So when we do that, you're going to have our total differential to be equal to, when you multiply here by xy of this, then it means that this will go off and the x will also go off. Then it will left with only what? Y. So we're going to have y times small f of u dx. Then when we multiply this aspect through by this function, then it means that the denominator will go off. We have x left, so plus x times big F of what? U, right? This dy, right? So our total differential is small f of u times y dx plus big F of u times x dy. Right. So don't forget that our total differential was amount to what? 0. So this is equal to 0. So we have small f of u times y dx plus big F of u times x dy is equal to what? 0. So you see, we've worked our way out. We've differentiated this equation, this integral equation, to have what? The integrating factor of the differential equation, right? So once we have the integrating factor of the differential equation, then it means that this our integrating factor that we had, of which we were asked to verify that it is an integrating factor, is indeed an integrating factor, right? Because we have proven, we have using that and this to show that the integrating factor of the differential equation is indeed that equation, right? So it means that that integrating factor is indeed an integrating factor. So that's that we have confirmed that the differential of this function, the differential of this integral of f, this is what? This is what we represented as what? U, right? So in as much as we are done, then it means that we have to make sure that this goes back to its original form, right? So this is, earlier on we said that u should be what? Xy. So we have to send it back. So we have f of xy dot y dx plus f of big F of xy dot x dy equals 0. So this is what? The original equation, right? So once this has been given, this has proven the integrating factor, then it means that we have confirmed this differentiating this equation. So thus we have confirmed that the differential of that function plus all over minus times d of xy all over xy plus ln into x over y is indeed equal to 0, right? So we have proven that, and it clearly shows right here. So now we can go ahead and fully solve the differential equation that was given. Okay, so let me write this conclusion before we start solving the full differential equation, right? So this clearly means that this we have here f of x y times y dx plus big F of x y times x dy is equal to 0. Thus the function that we named earlier on, phi of x and y, is a solution to the original to the original differential equation. And we can boldly say that mu of x comma y, or I of x comma y, equals 1 over xy into small f of xy minus big F of xy is indeed an integrating integrating factor. It's indeed an integrating factor. All right. So now let's fully begin with the differential equation. Let's start solving it, right? So we're going to solve that differential equation since the integrating factor is indeed an integrating factor. So we're going to solve that equation, which is x squared y squared plus xy plus 1, all multiplied by y dx plus x squared y squared minus xy plus 1, all multiplied by x dy. That is equal to what? 0. Okay, so we're going to solve this differential equation. Note, for our work to be easy, for us to make the work so easy, we have to let these product functions represent a variable, a single variable, right? So first of all, let u equals xy. This implies that from our earlier notice, we said that u should be equal to xy. So we use the product rule to differentiate, right? So that gave us, you differentiate x, then maintain y, right? So plus maintain x, differentiate y. We use the product rule here, right? So let's try to express the equation in terms of u and du, right? So if that is going to work, then recall that we said u squared should be equal to what? X squared y squared, right? And as well, u should be equal to what? Xy. Okay, so if we've okay, so now since we've recorded that u squared should be equal to what? S squared y squared, and u should be equal to what? Xy, then let's try to do that substitution into the differential equation. So we're going to have this to be what? U squared plus this to be what? U plus 1, all multiplied by y dx plus this is u squared minus u plus 1 multiplied by x dy equals what? 0. Okay, so what can we do here? What can we do here? You know, we are trying to express this differential equation in terms of u and du. So what can we do here? We know that du is equal to what? Y dx plus x dy. So we can do change of subject and make some notations a subject, right? So here we can say that y dx should be equal to what? Du minus x dy, right? We can say that du minus x dy should be equal to what? Y dx, right? So if that is true, then we can do that substitution in here. Are we okay with that? So let's proceed with that. So we're going to do that substitution. So we're going to put that this expression in place of wherever we see y dx, right? So we do that. We're going to have u squared plus u plus 1 multiplied by du minus x dy, right? Plus u squared minus u plus 1 x dy, right? And that should be equal to what? 0. Once we have this, then let's try to do some substitution. Let's u squared plus u plus 1 equals what? A. And also let b equals this, u squared minus u plus what? 1. Right, so we're going to have a y dx plus bx dy equals what? 0. So if we have this, then it means that from our previous discussion, we said that the u should be equal to this, right? So if that is true, then we can make y dx the subject. So making y dx the subject, we're going to have du minus x dy, right? So wherever we see y dx in here, we're going to substitute this, right? Wherever we see y dx, we're going to substitute this expression. So we're going to have a into du minus x dy plus bx dy equals 0, right? So we say that when we expand this, you're going to distribute the a to all the items in the bracket, right? So we're going to have a du minus ax dy plus bx dy equals 0, right? So ax dy and bs dy, we can group them because they all have dy and dy, right? So we have a du minus into brackets ax or k. We have x common to all, right? So we can bring x out. Then we have b minus a, right? B minus a or dy. Okay, so this is what we have so far. Now, how do we get b minus a? From here, we say that a should be equal to this and b should be equal to this. So we say that b minus a will be equal to u squared minus u plus 1 minus u squared minus u minus 1. Right? So we're going to have b minus a to be equal to u squared. We take off the minus u squared. Then this come on, let's do that is b minus a should be equal to what? This is b, so we have u squared minus u plus 1, right? Minus a, which is u squared plus u plus 1, right? So we're going to have that to be equal to u squared minus u plus 1 minus u squared minus u minus 1, right? So we can see that this take care of this and this also take care of this. So we're going to have b minus a to be equal to minus 2u. Okay, so we have b minus a to be what? Minus 2u. So we're going to substitute that into this, right? So we have a du plus x into minus 2u dy equals what? 0. So we have a du minus 2ux dy equals 0. All right, so this is what we have so far. Okay, so what can we do with this equation? So we can see clearly that we are trying to eliminate all the x so that we have an expression in terms of u and du, right? So let's come up here. Okay, so we have a du minus 2ux dy equals what? 0. So we can say that a du is equal to 2ux dy equals what? 0, right? We have equated them. So what can we do? Don't forget that we said u should be what? Xy. So since u is equal to xy, then we can do some substitution, right? So since u is equal to xy, then we can make x the subject from there, right? So making x the subject, we're going to have x equals u over what? Y. Okay, so we're going to substitute this into this, right? From at the beginning, we said that u should be what? Xy. So now we say that a du should be equal to what? 2u times x. Wherever we see x, we put what? U over what? Y, then times dy, right? So we're going to have a du to be equal to 2u squared over y dy. Okay, so we have an expression in terms of u and y, right? So what can we do from here? Okay, you see, this is over 1, right? So we multiply here by y, right? So if you multiply here by y, multiply here by y, this y will go off, right? So we have this, so we can say that u squared divide here, so that we go off with this. So we have ay du all divided by u squared equals what? 2 dy, right? So we can say that we have a out. No, we have to make sure that this a goes off because we are interested in du in terms of what? Y. So we want to make sure that y comes out. Then we have y over what? U squared. A over u squared, right? A over u squared multiplied by du, right? And that is equal to what? 2 dy. Okay, but don't forget that we said a should be equal to u squared plus u plus what? 1. Yes, we said that a should be equal to u squared plus u plus 1, right? So if we have a over u squared, then that means that we divide here by u squared, divide here by u squared, divide here by u squared. So we have a over u squared to be equal to 1 plus 1 over u plus 1 over u squared, right? So basically we are breaking it down. We will result into a simple differential equation, which is going to be the separable method. So now our a over u squared is this expression, right? So we're going to substitute it in there, y out. Then we have 1 plus 1 over u plus 1 over u squared, all multiplied by du equals 2 dy. Right, so now that we have this, what can we do? We have this expression now. So we are heading towards separable method, right? So with the separable method, we know what to do. So from here, we cannot use the separation of variables, right? We can use the separation of variables in here, right? So we can see that we have all these items are for u, right? So we have to take off this y from this left hand side. So we divide here by y, divide here by y. So this goes off. So we have 1 plus 1 over u plus 1 over u squared, or the u to be equal to what? 2 over y dy. Okay, so this is what we have now. So this is what we are coming to integrate, right? This is what we are coming to integrate so far. So all that we were doing, we're trying to get a function, a simple differential equation that we can differentiate, right? So now that we have this, we can integrate both sides. Integrate both sides, right? So we integrate this 1 plus 1 on u plus 1 on u squared du to be equal to 2 over u, 2 over y dy. We integrate that as well. So you know that when you integrate, let's try to express this differently again. So we're going to have integral 1 plus 1 on u plus u power negative 2 du equals 2 out 1 over u, 1 over y dy, right? So we do that from here. So from here, when you integrate 1, you're going to have, with respect to u, you're going to have u plus, when you integrate integrate 1 on u, you're going to have ln u. So you have plus ln absolute u, plus when you integrate u to the negative 2, you're going to have negative u to the negative 2 plus 1 divided by what? Negative 1, right? Divided by negative 1. And that is equal to 2 times integral of 1 on y is what? Ln y. So plus our constant of integration, right? So we're going to have u plus ln u minus u to the negative 1 equals 2 ln y plus c. So we're going to have u plus ln u minus 1 over u equals 2 ln y plus c. Okay, so this is what we are having. Yeah, this is what we are having. So this is our general solution. This is our general solution. But don't forget that u is equal to what? Xy. From our earlier definition, we said that u should be equal to what? Xy. So we're going to say that xy plus ln into xy minus 1 over what? Xy should be equal to 2 ln y plus c. Okay, so that is the end of this question number 1, as we have our final answer here. That is basically for question number 1. You see, this is our final answer. All that we were solving up and down, this is our final answer. Xy plus ln into xy minus 1 over xy equals 2 ln y plus what? C. And that is our final answer for question number 1. Now let's move on to question number 2. Okay, so with question number 2, this is the differential equation that we have. dy dx cos x plus y sine x equals cos cube x, right? Under this range, 0 less than or equal to x less than or equal to 2 pi. All right, we want to differentiate, we want to find the differential of this function. Then we sketch the graph of it, right? So first of all, once you see a function or differential equation of this form, begin to think of separation of variables or separation of functions. So this is basically trigonometric differential equation, right? So in here, we're going to say that dy dx, we arrange it properly, cos x dy dx plus y sine x equals cos cube x. This is the most easiest problem you can have in differential equations. All right, so in here, we know that we can divide through by cos x, and then we're going to have y sine x over cos x equals cos cube x over cos x, right? So we're going to have dy dx plus y. You know that sine over cos is tan x. So we have tan x. And that is equal to this. We take off one of this, and then we have this, right? So this is the simplified differential equation. Now, does this represent separable method, linear differential equation, or homogeneous method? Basically, we can talk about linear differential in here, right? So this, we can say that this is a linear ordinary differential equation because the degree are 1 and it's a first derivative, right? So this, we're going to say that this is of the form dy dx plus y p of x or p of xy equals q of x, right? In here, our p of x is the coefficient of y here, which is tan x, and our q of x is cos squared x, right? So we have all these informations. The rest is computations, and we know that how we can get our mu of x, because we are going to use the integrating factor, right? So we know that this of x and y is equal to an exponential of this, the x, right? So we're going to have this to be equal to integral the p of x, right? So we have integral tan x dx, and this is basically integral of tan x is negative ln into cos x, right? So we have negative ln cos x, that is integral of tan x. Okay, so note that. So this is a log function, right? Negative ln into cos x. And don't forget that one of the log properties says that if you have any function behind a log function, you can send it to the exponent, right? So we're going to have e to the ln cos negative x, right? So this is basically telling us that we have ln e times cos inverse x, and this is 1. We know that ln e is equal to 1, right? So we're going to have our final integration factor to be cos inverse of what? X, and that is equal to 1 over what? 1 over cos, and that is sec x, right? You know that 1 over cos is what? Sec s. Okay, so now we know our, so now that we have our mu of x to be sec x, then we come back and multiply it by the standard form of the differential equation that we have, right? So we're going to say that mu of x times dx dy dx plus y times x equals cos squared x, right? So we're going to say that sec x times dy dx plus y tan x equals cos squared x, right? So when we spread this, we're going to have sec x dy dx plus y sec x tan x equals sec x cos squared x, right? So in here, once you've done your correct simplification before you started multiplying by the mu of x, then when you get here, I'm going to say that this d dx times the y that you left off is when you picked the p of x, you left y off, right? So you're going to multiply that y by mu of x, right? And that is equal to the right hand side, okay? Sec x cos squared x. Okay, so that is how the left hand side simplifies. So we're going to say that this, the x, y times this is what? Sec x to be equal to sec x is basically 1 over what? Cos times cos squared x, right? So we're going to have d dx y sec x equals cos squared x over cos x, right? So we're going to have we're going to have d dx y sec x to be equal to cos x, right? So this is what we have at the moment. So we need y. Okay, so now that we have been able to separate it completely, then we can integrate both sides, right? So, but before we can integrate both sides, we have to make sure that the x is off, right? So we have dy sec x equals cos x dx, right? So now we integrate both sides, then this takes off this, so we have y sec x to be equal to integral cos x is basically sine x plus our constant of integration, right? So this is what we have. We need y so that it can be explicit. So we have this divide by sec s, this divide by sec x, right? So this cancels this, and we have y to be equal to, 1 over sec s is what? Cos x. So we're going to have 1 over sec x into sine x plus c, right? So this is telling us that we have y to be equal to cos x into sine x plus c. All right, so this is our general solution. Okay, so that's the general solution of the differential equation is y equals cos x into sine x plus a constant of integration c. Okay, so this is the end of the problem, but we are asked that we should sketch this solution. The result that we have, we should sketch it under this range 0 to 2 pi, right? So we have to basically get the values within this range, then use them to sketch the graph. But how are we going to get our constant? Well, we are going to pick a number 1 to represent our constant. So we are going to assume a value 1 to represent our constant c. So we're going to have cos x into sine x plus what? 1. We are doing that because we were not given any initials, right? If we were given initials, then we would have been able to find the constant of integration, but we were not given any initials. So we have to assume a value for c so that we can have the particular solution, so that we can find, we can graph our, we can do our graph, right? So the reason why we are choosing 1 is if you pick 0, okay, if you pick 0, you're not going to have both positive and negative, right? You're going to have only one side. But if you pick 1, you're going to have both positive and negative, right? So you can draw your graph. So let's pick the value. Let's say that c is equal to 1, right? So if c is equal to 1, then we are assuming, okay? We are assuming. So we say that y should be equal to cos x into sine x plus what? 1. So this is the equation that we are going to use to generate the value so that we can draw or sketch our graph, right? So let's dive into. Okay, so that is the table. I'm going to display the graph at the end of the video, so you can pause and look at the sketch. All right, so that is the end of the video. Thank you very much for watching. I really appreciate Okay, so this is the table, this is the S column, this is the S values, this is the first value for X, 0, and the first value for Y. Use it to sketch. Pi on 2, Y value is 0, pi, Y value is -1, 3 pi on 2, Y value is 0, and 2 pi, Y value is 1. So I'm basically going to display the graph at the end of the video, right? So you see the graph drawn nicely at the end of the video. Thank you very much for watching. I really appreciate your time. Please don't forget to subscribe, share with your mates, and I'm going to give you more updates. Until the next video, keep learning and stay inspired. Bye-bye.